Today I have the rather interesting task of Dr. Z is not here, so I have to both introduce the speaker and be the speaker myself. So I will do that. I guess so thank you all for coming. My topic is going to be somewhat similar to a talk that I gave in the seminar last year about partition identities. I have some new things to report, although I'll start off by kind of repeating some of the talk in case there's some people who weren't at the previous talk. And then I should say one other comment is it's not going to be very much on the actual proofs. It's going to be more on the end of the talk is going to be how one might prove this, even though we haven't finished it off yet. Some ideas. Hopefully, I will leave it open for some. If people want to think about this on their own and talk with me, I'd be glad to do that. Also, part of it is, hopefully the talk won't seem too hard to follow sort of thing, but part of it, in my mind, is kind of like the way that I came to realize stuff. So there's part of my personal journey going on in this, I guess. Okay, so without further ado, let me jump in. So let me just say, okay, we're talking about partition identities, so let me first just quickly say what are partitions. So I'm going to have a finite sequence of integers, all positive, lambda 1, lambda 2, lambda k, and oops, I'll make it strictly bigger than 0, that works. And I want them to add up, so I'm going to be partitioning some integer n, so they're going to add up to n. 7 plus 7 plus 3 plus 3 plus 3 plus 1 equals 14, 23, 24, so 7, 7, 3, 3, 3, 1 is a partition of 24. So one question we can ask based off of this is, how many partitions are there? And so we're probably looking for one nice answer to this is a generating function. There's a very nice generating function for the partitions. It's just 1 over 1 minus q to the j, and we're going to multiply these together for all j. Basically, 1 over 1 minus q to j, this term by itself is just a generating function for only using the part j. And so when we multiply them all together, we get the generating function for any parts that are allowed. Now, that's a kind of interesting question, but we already kind of answered it, so let's do something else. What happens if we restrict our partitions that we care about? So I might put some kind of condition on my partitions and say, hey, they have to fall into such and such a category. So, for example, what happens if I say in a partition I'm counting, I want all of the parts to fall into some congruence class. So I kind of unintentionally, but right over here, this is an example of a partition in which all the parts are odd. They all are congruent to 1 mod 2. So audience participation, how do I write down a generating function for this?
Just the j is over in the congruent class, right?
Yeah, that's all I have to do. So j, and I'll just write this in words. So there we go. That's nice and easy. So with this sort of trick, this sort of condition, I'm saying you can only use these parts. You can only use 1s and 3s and 5s and 7s and 9s, or I'm doing odds, but I'm not saying at all how the parts interact with each other. So I can also do some other ones that are more about how do the parts interact with each other. partition. So here is one. What happens if I say that you can only use distinct parts? So once I have a 5, I can't have another 5. Once I have a 7, I can't have another 7. Once I have a 4, I can't have another 4. So now it's not, I can put in anything, any part that I want into my partition, that's allowed, but now they're interacting with each other in some way. And then that makes things different. I could also have difference 2. So now this is like if I have, say, 5 in my part, not only can I not have a 5, but I can't have a 4, I can't have a 6. So these are adjacent parts that are at only difference 1 to each other, so this isn't allowed. And so a partition that satisfies this difference 2 condition might look more like 9 plus 7 plus 4 plus 1. So the differences here, so I can't repeat because that would be difference 0. Differences here are 3 and 3 and 2, so that's all difference. I say difference 2, I really mean difference at least 2, but that's what's going on here. So these are a couple of the ways I can have the parts. So there's kind of 2 big kinds of restrictions. Restrict the types of parts I'm allowed to use, or say I can use any parts that I want, but I have to make up some rules about how they interact. Any questions so far?
Well, distinct parts means you've got to put it in the numerator instead of the denominator,
Right, yeah. So, so there is some special stuff when we come up with, Euler's theorem, which I'm about to put up, gets proved differently than all the other theorems that we care about. So let me just say what I mean by a partition identity. Partition identities. So these are basically 2 different classes of restrictive partitions that are equinumerous with each other. So, for example, I'll give an example right here. The most famous one is Euler, which says number of partitions into odd parts equals number of partitions into distinct parts. And of course, I'm kind of suppressing some notation here. Really what's going, I should be saying number of partitions of n into odd parts equal number of partitions of n into distinct parts for all n. That's, the board gets filled up if you try to write that every single time. But so this is the oldest partition identity. Goes back, mid 1700s. Although I should say, so Euler wrote down a series equation that implied this. He didn't actually write this down himself. The partition interpretation wasn't until some time later.
Do you happen to know when someone interpreted Euler's identity in terms of partitions? I don't know that.
I think it's late 1800s.
Mm-hmm.
That sounds probably like Glacier or somebody was the guy to do it. But a kind of similar story, although more compressed time frame, is Ramanujan identities, which there's a pair of them. The first one says, I'm just going to say, instead of odd parts, I'm just going to say, so 1 and 4 mod 5. That's my congruence class here. And so why did I use difference 2? So the number of partitions into parts congruent to 1 or 4 mod 5, same as the number of partitions that satisfy the difference 2 condition. There's 2 Ramanujan identities. And so here we have one, so this is 2 and 3 mod 5. And so here it's difference 2 plus no 1s. So you're not, so The same thing here, but there's an extra, we'll call this eventually, we'll call this an initial condition. So some weird base cases here, so you can have 2s, 3s, 4s, 5s, but for whatever reason, don't worry too much about, we're banning 1s. And so, once again, the story goes here to the interpretation. L.J. Rogers discovered this in 1895, improved it, but nobody read the paper. When Ramanujan showed up in England in the 1910s, he rediscovered it, he found Rogers, they provided a new proof, but once again it was just a generating function proof, and I think it was Major Kanade who was the one who provided the interpretation, although that was just a couple years afterwards. And the third one, I guess I'm counting this as a single identity, same thing basically, but the third one I want to talk about is the Caporelli identity, the first one here. And so the product side is 2, I'm going to start writing plus or minus 2 plus or minus 3 mod 12. So note here, I could have written this as plus or minus 1, I could have written this as plus or minus 2. And on over here, this equals, so I have to be careful with off the top of my head, lambda I minus lambda I plus 1. So I have a difference 2 condition. I also have if lambda I minus lambda I plus 1 is at most 4, then lambda I plus lambda I plus 1 is congruent with 0 mod 3, and there's no 1s. So this is from 1990, give or take 2 years or so. On either side, Caporelli was actually a Rutgers PhD student studying under Professors Lepowski and Wilson. He came up with this conjecture in his study of Lie theory, and eventually provided a proof of that through Lie theory. George Andrews provided a proof of this. He provided the first proof of this, and that was through more traditional partition theory methods. But right now I'm not really worried about the proof techniques. So just here are these are what partition identities usually look like. Almost always we're going to have congruence class over here. And we'll call this is the product side. It's a product side because the generating function is a nice product, as Pat observed earlier. Then over here I'll just call this the sum side. The sum side is basically going to have to do with how do the parts interact with each other, and we might have some initial conditions down here. So let me just write up kind of formally. So Shashank Kanade and I undertook a computer search to look for discover some new ones of these. So the sum sides, we have difference at a distance. Here are some conditions that we're going to put. Lambda I minus lambda I plus A. So here's one condition with 2 parameters, A and B.
Of course, there are vastly many identities that have been studied for.
Right. Yeah. This is not.
These are the ones you want to focus on.
Right. Yeah. Go.
But it's not clear from the vastly many that are known why they're there and not other ones.
Yes.
You're on the edge of that research.
So yeah, there are very many partition identities out there, and we'll discuss some more known ones throughout the talk. This should just kind of give some flavor for what inspired us. What do they typically look like? How can we generalize this? So one condition we've seen this come up. We can make this. I make A equals to 1, I stick a 1 here, this is distinct, I stick 2, here's difference 2, and so on and so forth. Inspired by this Caporelli sort of condition in here. we have what we call congruence at a distance. So this is if lambda I minus lambda I plus C is less than or equal to D, then the sum of the parts has to be congruent to something mod something. And then we'll have some sort of initial conditions, like this whole no ones business here, no ones was also here. So this is like all parts are at least G and at most H copies of G. And so we sat down on a computer, ran this a bunch, there are, let's see, 1, 2, 3, 4, 5, 6, 7, 8 parameters. You know, run this for all reasonably small combinations of A through H, and just brute force calculate out the sum sides of these. I won't write this down in the interest of time, but there exists a nice algorithm. If you have a sum side, it will factor it and say, does this look like a product side? A nice product side. And so we can kind of test for that. Yes, it is a nice product side. There might be an identity here. No, this is not a nice product side. There's no identity here. And so after running all of this computer stuff, we came up with some discoveries. So let me just show off here. There are 6 initial ones I reported on last time I gave a talk here. So let me just run through the notation. So this star 2 and star 3, these are like the difference at a distance conditions going on here. This triangle A and box A, these are congruence at a distance, and they're always dealing with mod 3 here. And I'm sticking this A here so I can plug in 0, 1, or 2 for whatever I feel like here. So 6 identities, 4 of them are on this board. So I1, I2, and I3 all kind of go together. They're all symmetric, mod 9 identities. And then the sum sides here are going to be star 2, so that's difference 3 at distance 2. And then triangle 0, which that is if adjacent parts are within one of each other, their sum must be 0 mod 3. And then we also have our initial conditions. So no initial conditions for this one. You're not allowed to use 1s here. You're not allowed to use 1s or 2s here. So those were our first 3 identities. Conjecture identities. No worries yet. I4.
Are they still conjecture?
Still conjecture, yeah. Still open. I4, 2, 3, 5, or 8 mod 9. So now these are asymmetric. So that's a little bit different than the ones we've seen so far. Star 2, triangle 2. So now if they're within one of each other, the sum is congruent to 2 mod 3. So that's kind of different. There's something to trip over here. And no ones. So these are 4 mod 9 identities. And then we had a couple of mod 12 identities, which I won't. You can read the congruence class on each one of them. Now these mod 12 identities, it's difference 3 at distance 3. So we changed the distance from 2 to 3 in this condition. And now we're using this if parts at distance 2 are within one of each other, their sum, including the intermediate one, has to be, in this case, 1 mod 3 or 2 mod 3, and you can see the initial conditions. So you can't have 2 1s, you can have 1 1, you can't have 2 1s. Down here you can't have any 1s, and you can't have 2 2s. So that's kind of where we were at the end of the last talk. And so for the rest of the talk, I'm going to be discussing a couple of things, potentially new ways to search for new identities, and also how we might think about proving these. And so, I guess the next thing to say is back in June, I had an opportunity to go visit George Andrews at Penn State, so kind of a partition theory guru. And in our conversation, he made some very interesting points to me that kind of really reshaped the way that I view partition identities. Two important things here. Number one, the thing that he observed to me was that, well, I guess there are two big observations. But the first thing is take a look at like these last three identities. So the first three form a nice happy family. Everybody can believe that those three are related in some way to each other. But then like this I4, this fourth one, it kind of sticks out like a sore thumb. Like there should be something else going on with it. It needs a friend, basically. And ditto for this one, ditto for, these both have 7 things mod 12, but if you stare at long enough, you can't really come up with a way to turn these numbers into these numbers in some sort of nice way. And so, there just are a lot of things that are unnatural going on here. And so as Andrews explained to me, I should be thinking about, there should be, if the part, I'm kind of paraphrasing, I don't know what words he exactly said, but it's basically, if math works the way we think it does, there should be one, and there should be friends of these, friends not being a technical term here, but, and they should be have the opposite congruence conditions. So if this one is 2, 3, 5, and 8, where should be one that's 1, 4, 6, and 7 mod 9. And the sum side looks somewhat similar. So that was the first kind of thing too.
And whatever the sum side turned out to be, it wasn't in your initial search.
Right. And so that's the second point.
Yeah.
The second point that Professor Andrews made, which is just realizing like I needed to broaden my thoughts on what initial conditions were. So it's like if we let's take a look here. So I basically, the way we were looking for initial conditions were that all parts had to be at least something, at least, we said at least 1 if we didn't want to make that bigger, or at least 2, or at least 3. And whichever the smallest thing was, whatever our bottom thing was, we said there can be, there's some sort of cap on how many there can be. So that works great for like over here. So like this no ones, that comes from saying all the parts have to be at least 2. And then no 2 plus 2, say okay, so their smallest part is at least 2 and there can be at most 1, 2. So that's how this framework translates into, hey look, I found that. But let's take a look at this framework and so it would work here on Caparelli, but didn't have time to pull this up, but Caparelli had a second identity that is similar in spirit, and the condition was no 2s, right? I think. Yeah.
I think so.
Yeah. So the condition there, it was a similar sum side, but the initial condition was no 2s. You could have 1s, you could have 3s, you just couldn't have 2s. And so the way that we should be thinking about initial condition is just say, initial conditions, let's just say forbid. So we're just going to forbid some hopefully small set of subpartitions. I won't carefully define that, but hopefully that should be obvious. So forbid some finite, hopefully small set of subpartitions. So we can say, okay, in I3 case, we're forbidding both 1 and 2. In the I6 case, we're forbidding 1 and we're forbidding 2 plus 2. Now this is harder to teach a computer, like that when we're making, sets and searching over that. that's going to be a lot more possibilities than in our previous nice framework. This is harder, but if payoff is we find more conjectures, then that's a kind of worthwhile payoff. And so sure enough, we were able to find a couple more. So these are new conjectures since the last time we gave this talk. So, okay, for prime, sure enough, there is a friend for this one. That is 1, 4, 6, and 7 mod 9. And then the conditions here are the same difference at a distance condition. Let's see, so the congruence flips from 2 to 1, no surprise there. And then the sum side, or the initial condition are no 2 plus 2. So you're allowed to have 1 in it, you're allowed to have 2 in it. 2 plus 2 would be allowable by the other sum size conditions, but we're banning that. There's also friends for I5 and I6, which are 1, 2, 5, 6, 8, 9, 11 mod 12, and 1, 4, 5, 6, 7, 9, 10 mod 12. You can verify for yourself that these are just opposites of each other, so if I just negate everything in here, I get list of congruence classes. And then over here, no surprise, I flip signs here. So this is,
since it's impossible to discover sum sides experimentally from prime sides, unless you
yeah,
so you just expanded the domain.
right.
So
We just expanded the domain of what our sum sides look like. So no 2 plus 2 plus 1, no 2.
But you didn't have a large search pool because you just had to try things sort of like that.
Right, so right. As it turns out, like we didn't have to, there's nothing in when I said forbid some set of subpartitions. Well, in all 3 new cases here, well, the set consists of 1 element, but not very exciting. But we looked for ones where there were more than one thing in the sub. Didn't turn up anything. Not saying there's any, not anything there, but so far, it's always maybe we try, put this idea together with this idea in some way we haven't thought of before. There will be some